Welcome to your third and final installment for Chapter 14. And we're going to start with talking about reaction mechanisms, and then we'll finish with talking about catalysis, so the use of catalysts in reactions. So reaction mechanisms are a way for us to explain or to show how a reaction can happen in ways that are not immediately obvious. So given this particular reaction here, this nitrogen monoxide plus oxygen making nitrogen dioxide is our smog equation, right? This is one that we started off with Chapter 14 talking about. Now, in order for this to happen exactly the way it's been written, we would need, if we think about things in terms of collision theory, we would need to have three individual molecules coming together in exactly the right way at exactly the right instant with exactly the right energy. This is probably not likely. Okay, thinking about how many different molecules are floating around in the air, and for these three molecules to come together at exactly the right time with exactly the right conditions is probably not very likely. Okay, so how do we explain this? This does happen. We know it does. We know that smog is made. It's explainable by reaction mechanisms. A reaction mechanism. So instead of thinking about this as one simple process, we take it as a step-by-step process. We break the reaction up into multiple smaller reactions, and the step-by-step process is made of what we call elementary reactions. Okay. Elementary reactions is a particular term that we are going to give to a certain type of reaction. So, sort of generically, we can talk about them in terms of unimolecular elementary reactions, in which case we have a single chemical species going to products. We can talk about bimolecular elementary reactions, where we have A plus B. We have two items, two reactants going to products. So unimolecular is one, bimolecular is two, trimolecular would be three. Okay, and what's important about elementary reactions is that the reaction order for elementary reactions is the same as the stoichiometry. Okay, this is the one place where this is true. Okay, if you're told that you have a series of elementary reactions, quote unquote, those elementary reactions will have the same order as their stoichiometry. Okay, in all the other examples we've been through, the order is determined by experimental values. With elementary reactions only, we can do order by stoichiometry. Okay. Another important thing about reaction mechanisms is that one step will be slower than the others. Come on. Okay. What's important about that, and we're going to star this and put it in red because I want everyone to focus on this idea. The slow step is the rate determining step. Okay, the entire reaction, the rate of that reaction will be determined by the slow step. Okay, it's sort of like the analogy that I like to give is that it's sort of like imagine you're on family vacation and you have parents and brothers and sisters and maybe a cousin or two all staying together in a hotel, maybe hopefully not the same hotel room, but all staying together, and you want to go out someplace. There's always one person in that group that takes longer than everyone else to get out of the hotel. How fast you get to your destination is dictated by that one person that takes forever to get out of the hotel. So in reaction mechanisms, the rate of the entire process is determined by the slow step. All right? So let's look at a reaction mechanism. So if we start with a reaction that looks like this, hydrogen gas plus some iodine chloride, ICl gas, that should be a 2 there, gives us some iodine gas, I2 gas, plus some hydrochloric acid gas. Okay, here again, looking at this reaction, if I take those 3 molecules in the reactants, it's not terribly likely that they're going to come together all on their own as they are. So let's break this apart into a mechanism. So our mechanism will look like this. We'll have reaction 1. We're going to start with some hydrogen gas. We're going to mix it with some ICl. And we'll have hydroiodic acid as a product and HCl as a product. Okay? That's going to be our slow step. And we'll give that a rate constant of K1. All right? Our second step, we'll have our HI plus ICl again. Will give us our desired products, some of them anyway. This will be a fast step. We'll give it a value of K2. Okay? So if I take these two and I can check my work, okay, I can double check that if I add these two, if I combine these two reactions, I should get this process as my answer. So remembering how to combine reactions, anything that's the same on both sides, you subtract. Anything that's the same on the same side, you add, right? So in my top reaction, I have HI as a product. In my bottom reaction, I have HI as a reactant. Those subtract, so they go away, right? I have 2 ICLs as reactants, and I have 2 HCLs as reactants. Everything else drops down. So if I combine these reactions correctly, I should end up with the same thing as my overall reaction, right? So K1, reaction 1, that rate constant is the rate determining step because it's the slow one. Okay, so K1 is rate determining. Okay, that rate constant will be the rate for the entire reaction. Okay? And the other thing to remember is that because they are elementary processes, we can write rate law equations from the stoichiometry. It's a lot of words to write. Okay, so rate for reaction 1, let's make this in blue, will give us K1, and our stoichiometry from reaction 1, let's take a look at it. Reaction 1 has 1-to-1 hydrogen gas to ICl. So they both have orders of 1 because they are elementary. HCl to the first, ICl to this first. Okay. And then rate 2 for reaction 2, again, we have stoichiometry of 1 and 1. So I'll have K2 HI to the first and ICl to the first. Okay? So I can, whatever I want, if I can write a rate equation for anything, and if I'm told that it's an elementary process, my order will be based on the stoichiometry. So let's take a look at what a reaction progress graph would look like. We did this with our collision theory and our transition state theory. But we have 2 reactions going on here, right? So let's take a look at what a graph of that would look like. Right, so if we have our progress on the x-axis and our energy on the y-axis, this reaction is going to have this form. It's not a terribly smooth plot, but let's take a look at what we are seeing with this graph. So we still have our reactants at the beginning and our products at the end. Okay. We have our, and since we have 2 reactions, we have 2 activation energies. All right, so I've got the activation energy for reaction 1. And I've got the activation energy for reaction 2. Okay. Notice that the way I've drawn this, and it was sort of serendipitous that I did so, the activation energy for reaction 1 is larger than that of reaction 2. And taking a look at our reaction mechanism, our slow step is reaction 1. So this is how this is going to play out. Your slow step will almost always have a larger activation energy. That's why it is a slower reaction. Okay? So we still have our, we can also talk about our overall energy of this reaction, our delta H. Exothermic. Now what's interesting about this particular scenario is because we have 2 reactions, we have this trough in the middle, right? And in that trough, what you find are your intermediates. Okay, in this case, our intermediate is the, I have to come look again, is the HI. And I'll talk about that here right now. Okay, so looking at our reactions here, an intermediate is something that is made in the first reaction and immediately used up in the second reaction. So in this case, the one that is made in the first reaction and used up in the second reaction is the HI. So HI in this set is the intermediate. Okay. The HCl is made in both reactions, so it's not an intermediate in this case. All right. So let's talk about how to determine a rate law from a reaction mechanism. An overall rate law. And we can write rate laws for the individual steps, but what's the overall rate law? Okay. So important things to keep in mind. The rate is controlled by the slow step. And therefore, the rate law for the overall reaction is also the rate law for the slow step. Okay, so once you determine the rate law for the slow step, you also have the rate law for the overall reaction. Okay, so in the case of our reaction up here, our slow step is reaction 1. So for the overall reaction, the rate law for the slow step is the rate law for the overall reaction. Okay. So let's take a look at a slightly more complicated scenario. Okay. When we have elementary reactions and they only go one way, slow step is the overall rate law. Great, fine. Okay. But let's take a look at something slightly more complicated. So the rate law when there's an equilibrium followed by a slow step. Right? So let's take a look at a scenario that looks like that. So we have reaction 1 is 2NO in equilibrium with N2O2. Okay, so the forward reaction will have a rate constant of K1, and the reverse reaction will say has a rate constant of K2. Okay, and this one is the fast step. All right. Then we also have a second reaction, which is N2O2 plus O2 gives us 2NO2. Okay. This one will have just a forward step with a value of K3, and this is the slow step. So if I combine these reactions, my overall reaction looks like this. 2NO plus O2 gives 2NO2. This is our Smog equation, right? So the overall rate law is still the slow step. So we would say the rate equals K3 N2O2 times O2. And they're elementary steps, so elementary reactions, so we can keep the stoichiometry or the order based on the stoichiometry. But here's the trick. Here's the trip up, I should say. Can't have an intermediate in your overall rate law. Okay, so looking at our two reactions here, N2O2 is made in the first reaction and then used up in the second reaction. So the N2O2 is an intermediate. And we can't have an intermediate in the overall rate law. Right? Because we don't start with the intermediate, we don't end with the intermediate. It doesn't give us any useful anything to work with. Lucky for us, there's a way to get around that. Okay, so the slow step still governs the rate, but with N2O2 being an intermediate, we need to do something about that. So we're going to use substitution. Right? And what this is based on is that at equilibrium, forward and backward reactions have the same rate. Okay, so our forward reaction in the first step, our first step was in equilibrium, so our forward is 2NO with K1 gives us N2O2. So we can write a rate law for that. Rate equals K1 NO squared. Squared because it's an elementary reaction, so we can have the order based on the stoichiometry. And then our backward reaction will have N2O2 with K2 becoming 2NO. Okay? So if the rate equals K1 NO squared and the rate equals K2 N2O2, then I can write this as K1 NO squared equals K2 N2O2. Because they both equal the same thing, therefore they equal each other. Okay? So now, let's rearrange this to find N2O2. That's our intermediate that we want to get rid of from our overall rate law, right? So if I rearrange that to get N2O2 all by itself, what I'm left with is N2O2 equals K1 NO squared over K2. Now we substitute back in to our overall rate law. So our overall rate law was rate equals K3 N2O2 times O2, right? So I'm going to take this and plunk it in right here in place of the N2O2. So now my new overall rate law will look like this. Rate equals K3 and our substitution K1 NO squared over K2 times O2. Okay? And we can simplify this a little bit. Do a little math hand waving. If we say let capital K equal K3 times K1 over K2, then our rate law becomes simpler. And the overall rate law now is capital K NO squared O2. Okay, so our K3 times K1 over K2 is this piece right here. Okay, so we're just doing a little symbolism substitution there to simplify our situation. Okay, so this would be our overall rate law with no intermediates. Okay, we can't have intermediates in the overall rate law because they appear and then they immediately disappear. Okay, so important takeaways for reaction mechanisms. 1, they're made up of elementary processes. 2, for elementary processes, their order is based on the stoichiometry. 3, probably most important, the slow step is the rate determining step for the whole thing. And 4, if you have an equilibrium, you need to make sure that you don't end up with an intermediate in your overall rate law. If you do, you need to perform some substitution. Okay, so our last topic for chapter 14 is catalysis. Okay, or the introduction of a catalyst. Now, there are 2 types of catalysis. One is called homogeneous catalysis, which is done in solutions. Okay, so all liquid mixture, right? The catalyst, everything involved with the reaction is all in a liquid mixture. And there's also heterogeneous, which happens at a surface. Okay, so that's how you can tell the difference. If you're talking about a liquid solution where everything's happening, homogeneous. If you're talking about a catalyst that is a surface and the reaction is happening on the surface of something solid, you have heterogeneous catalysis. So let's take a look at what catalysts do for us. Okay, catalysts speed up reactions. Great. How do they do that? Catalysts speed reactions up by lowering activation energy. Okay, that's a very important topic. Catalysts don't do anything for the reaction other than lower the activation energy. So remember when we were looking at the reaction profile for a multi-step reaction, the slow step had the largest activation energy. So if I were to lower that activation energy, that piece of the reaction would speed up. So if I have a reaction profile that without a catalyst looks like this. Okay, we have our transition state. We have our activation energy, right? And we have our delta H, okay? With these being the reactants and products. All right, so just based on the shape of this graph, we can tell that it's an exothermic reaction because our products have less energy. Great. So this is what this looks like without a catalyst. Now, if I add a catalyst in, what happens to our graph is this. Okay. Our activation energy is now significantly lower. Okay. So with a lower activation energy, I will have a faster reaction. Okay. So catalysts, so when we're talking about adding catalysts to a reaction mechanism, catalysts do not appear in an overall reaction equation. And we're talking about when we combine our reactions, the result of that is should not have a catalyst appearing in it. Okay, and we'll see why here in just a minute. So let's take a look at two reactions. So looking at the decomposition of formic acid. Okay. So normally we have formic acid, which has a general formula to it, which looks like this. So to decompose formic acid, what has to happen is this bond has to break. That hydrogen moves over to there. Okay, and then it further decomposes. The result being something that looks like a reaction that looks like this. And it becomes carbon monoxide and water. Okay, so this is very slow. Okay, it takes a lot of energy to break that hydrogen bond and move it over. Okay, so, but if we acid catalyzed it, so if we add some acid to this scenario, we now have a solution with hydrogen ions. This is how the reaction takes place. So we have our formic acid, right, plus some acid, some H plus ions. Okay, so what's going to happen here is that hydrogen ion is going to do what the original hydrogen did, but without having to break that bond. So what we have is an intermediate. And I will not expect you all to be able to draw out this reaction mechanism. This is just an example of how a catalyst can be used. Right? So then we have this plus our H2O. and then this positively charged thing breaks apart into hydrogen ions and our and our carbon monoxide. Okay, notice we have hydrogen ions in the reactant, and then after the reaction is completely done, we get our hydrogen ions back. Okay, so the hydrogen ions sort of help the reaction along, but whatever catalyst we put in, we'll get the catalyst back out at the end. Okay, and this is homogeneous catalysis. Because all taking place in solution. Okay, in this case it's a liquid solution, but you could have a gaseous solution as well that would fit the bill. Okay, as long as you're dealing with a mixture and nothing's happening on a surface. Okay, so let's talk about how heterogeneous catalysis works. And heterogeneous catalysis may sound like it's a little bit bizarre, but in reality, all of the cars that we drive utilize heterogeneous catalysis in their exhaust systems. Okay, so heterogeneous catalysis happens at a surface. Okay, so there are 4 key parts to the way heterogeneous catalysis works. Steps, if you will. So step 1, we have adsorption of reactants. Okay. And if you're not familiar with the term adsorption, really this just means things are sticking to the surface. Okay, absorption with a B is something becoming part of something else. Adsorption with a D is sticking to a surface. Okay, they're 2 different terms. It's not actually a handwriting mistake. It is meant to be written that way. All right. So step 2 is diffusion of reactants along the surface. Okay, our reactants, once they stick, are going to be able to move to new locations so that they can react with something else. Step 3 is we have reaction at an active site. Okay, and when we have that reaction, we form adsorbed product. Okay. And then step 4 is desorption of those products, so unsticking. So the way heterogeneous catalysis works, the way that it goes about lowering activation energy, is imagine back when we were talking about collision theory, and the idea that in order for a reaction to happen, the reactants have to come together in the right orientation with the right energy in order for a reaction to happen. Sort of statistically, that's not terribly likely, okay? So, especially when you're dealing with a lot of different things going on. What heterogeneous catalysis does is by providing a surface, you're basically providing a ready-made environment for the reaction to happen. So reactants can only stick to the surface in a certain orientation, and then when they move to the active site and meet up with other reactants, everyone's already in the correct orientation. So there's less need for any kind of moving or shaping or anything of that nature. It sort of provides a ready-made environment for the reaction to happen. And then once the reaction happens, then it will release the products. All right, so let's take a look at an example from the real world, which are catalytic converters. Now, if you're like me, when I was younger, I used to think that it was something that converted catalytes, which is kind of ridiculous. But as a scientist now, I understand that it's a converter that uses catalysis, okay? And it converts harmful carbon monoxide and nitrogen monoxide to CO2 and NO. Or N2, excuse me. Now the CO2 is not great, but it's less harmful to us as humans than the carbon monoxide. And the way it does this is it uses a rhodium metal catalyst. Rhodium catalyst. Okay, so let's take a look at this sort of pictorially. So imagine the inside of your catalytic converter, and it has a plate of rhodium, which has the symbol RH. Okay, and on that rhodium, we have some carbon monoxide comes out of the engine and comes up to the rhodium, and it sticks. So we have our carbon monoxide, and it's stuck to the surface. And we have our nitrogen monoxide, and it's stuck to the surface. Okay, so our step one is the adsorbed products. Okay, so this is the adsorption step. Okay, next is the diffusion step. Oops, not RB, RH. So our carbon monoxide is stuck down, and we get some oxygen moving along from the nitrogen monoxide. So things are breaking apart, staying adsorbed, and moving towards each other. Okay, so this is the diffusion. Things are actually moving along the surface. All right. And then our last two steps, sort of all in the same step, what we have is we've got our carbon bonded to an oxygen, and it's met up with another oxygen. We have our two nitrogens met up, and we have another set of these. And so what we get is that desorbs as CO2, this one desorbs as N2, and this one desorbs as CO2. So this last step is actually both of the last steps. This is reaction and desorption. Okay, so heterogeneous catalysis requires a surface. Homogeneous catalysis happens in a mixture. All right, so let's take a look at what a catalyst looks like in a chemical equation. All right, so let's identify the catalyst. right? Given a set of equations. So let's say equation A, H2O2 plus I minus gives us OI minus plus H2O. Slow step. Equation B, or reaction B, and this one is a fast step. Okay, so if I combine these two equations, we subtract the things that are on opposite sides from each other. Okay, so our I minus is the same on both sides, so that goes away. Our OI minus are on opposite sides, so they go away. Our H2Os that are both on the right-hand side, those will add, and our peroxides, both on the left side, those will add. So we have our overall reaction C of 2H2O 2 yields 2H2O plus O2. Right? So let's take a look and see if we can find the catalyst. So the catalyst is something that we put in as a reactant and we ultimately get out as a product. Okay, and in this case, that is going to be the I minus. Right, so we put I minus in at the beginning and we get it out at the end. Right, so I minus is the catalyst. The OI minus is the intermediate. Okay, so the OI minus is made in the first reaction and then used up in the second reaction. Okay, so let's take a look. What are the rate laws? All right, so for reaction A, the rate law will be rate equals, and these are elementary reactions because they're part of a mechanism. So the rate equals, we'll call this K1, H2O2 times I minus. Reaction B, okay, and then overall, the rate law is the slow step rate law. Okay, and our slow step was reaction A, right? Okay, so pretty straightforward. Now let's take a look at one other factor. I said that a catalyst will never appear in an overall equation. Okay, this equation C, that's our overall equation. I minus does not appear in that overall equation. Okay, so we're following the rules. A catalyst should not appear. And the reason for that is that if we combine our equations correctly, I minus is a reactant in the first reaction and it's a product in the second reaction, so they should cancel each other out when we combine equations. Okay. Now, I hate to do this to you, but I did say that this would be the last thing, and that was a lie. So I inadvertently skipped over a rather important piece of the notes, and we're going to come back in the notes and find that and go over it. Let's see. Okay, so coming back to activation energy. And we need to take a look, and I didn't mean to skip this, I do apologize. But we need to take a look at how activation energy, rate, and temperature are all related. Okay, activation energy, rates, and temperatures. Okay, so generally, heat, sorry. Heat things up to speed them up. Okay. If you want to speed up a reaction, add some heat, warm it up. Okay, make it warmer. Now we have an equation that relates activation energy, rate, and temperature, and it's called the Arrhenius equation. All right, I'm going to write it down so that I can show some graphic of it, but you really won't be using this particular equation. But it does lend itself to how we get to the one you will use. All right, so the Arrhenius equation looks like this. We have a rate constant equals another constant, A, times E to the negative EA over RT power. Okay, and A is a constant for T, so at a given temperature, activation energy at a given temperature, and R is the gas constant relating to energy, so 8.314 joules per mole Kelvin. Taking note that we are in kelvins for this, okay? So if we take care of that E action, so in order to get rid of the E, we take the natural log of the entire equation. So we can rewrite this as natural log of K equals negative EA over RT plus the natural log of A. Now guess what? That part is the same thing as saying EA over R times 1 over T. So this could be Y equals mx plus B, right? So natural log of K would be Y. Negative EA over R is our slope. 1 over T is X. And natural log of A is our B. Right? So if I plot this as natural log of K on the x-axis, or the y-axis, excuse me, and 1 over the temperature on the x-axis, we get a linear plot, with the intercept being the natural log of A and the slope equals EA over R. Pretty handy. Okay, so if we want to talk about changes in temperature and how those relate to K, this is going to be your more useful equation. Changes in K to changes in temperature. Okay, so we have a wonderful equation that I'm sure you're all going to know and love and tell all your friends about. And it looks like this. So we have natural log of K2 over K1 equals EA over R times 1 over T1 minus 1 over T2. Okay, so we have a rate constant relating to a temperature, and we have two of each. Okay, so K1 is related to T1, K2 is related to T2. Okay, and remembering temperature in kelvins. Okay. So let's take a look at how we're going to apply this, and I promise this will actually be the last thing for this video. Okay, so let's say that we have a first order reaction. We have N2O5 decomposing to N2O4 plus oxygen. Okay. So we have some information. We're going to be given some information. We're given the half-life is 2 hours. We're given the activation energy is 1.06 times 10 to the 5 joules per mole. We're given K1 as 3.46 times 10 to the minus 5 inverse seconds. Our temperature that goes along with that is 298 Kelvin, our room temperature. Okay? And then R is a constant, it's the gas constant, 8.314 joules per mole Kelvin. Okay? So our task, given all this information, is find the temperature at T1 half. Okay? So in essence, we're looking for T2. Okay? Because we have everything in here except for T2. Okay? So let's go and get into that. Okay? So we're told that it's a first order reaction. Okay? In order to find T2, we need K2. Okay? We're given a half-life and we're told that it's a first order reaction. So we're going to do this from first order half-life. Okay? So T1 half, 0.693 over K, right? Rearrange, and I get K equals 0.693 over T1 half. Okay, now keeping in mind, let's take a look at K1. Notice that K1 is in inverse seconds, right? So we need to make sure that all of our units match. So we're given a half-life in hours. So 2 hours equals 7,200 seconds. Right? So K2, so the K at the half-life, 0.693 over 7,200 seconds equals 9.63 times 10 to the minus 5 inverse seconds. Okay? So now that we have everything in our equation except for T2, all we have to do is plug in the values. Right? So what we'll have is natural log of 9.63 times 10 to the minus 5 inverse seconds divided by 3.46 times 10 to the minus 5 inverse seconds. Now I want to remind you that this is a quantity. Okay, so do the division first, then take the natural log of that value. Okay, it'll be really easy to say natural log of 9.63 and then divide by 3.46. You need to make sure that you take that as a quantity and then take the natural log. So equals our activation energy, 1.06 times 10 to the 5 joules per mole, divided by our gas constant, 0.314 joules per mole Kelvin, times 1 over T1, 298 Kelvin, minus 1 over T2. Okay, and if this algebra scares you, I'm sorry, but this is a pretty common type of problem. Okay, so we work out all this arithmetic, and I'm going to show a little bit of the steps along the way. We'll have over here 1.024 equals 1.27 times 10 to the 4 inverse kelvins times 0.00336 minus 1 over T2. .024 equals 42.7 minus 1.27 times 10 to the 4 inverse kelvins divided by T2. All right, and we solve for T2, and voila, is 305 kelvins at T1 half. Okay, so it's a little bit involved. It requires you to be able to manipulate equations and utilize equations in tandem with each other. But I have no doubt that you will all do splendidly. And that does officially do it for Chapter 14. That was our last topic. And I hope that everything goes well for you. Please let me know if you have any questions. I am